Anyway, this talk is what we have been waiting for, and the grammar error is intentional. But first, I'm software engineer in Woven at Toyota, starting next week, actually. And I'm co-chair of Evolution Working Group in ISO C++ committee and chair of study group for compiled time programming. And yes, 2 days ago, we pushed a reflection to Evolution. So don't ask me about it. You know me for CTRE. I did talk 2019 and 2018 about it. And Lightning updates, I did talk last year. Also about CT-hash, which is compile time SHA-2 and SHA-3 implementation. It was fun implementing. I actually wanted to learn how to write these functions. So I implemented them in compile time. And cocurl. And that's a hint, because that's the talk today. Because I love JavaScript. And I know I'm on wrong conference, but I love JavaScript. How many of you love JavaScript? OK. 3, 4 hands. Great. Thing I love about JavaScript is you can easily prototype in it, and you can easily get done what you want without dealing how I will work with this socket and how I allocate something. It just works most of the time. So at the committee meeting in Varna and at CPP Now conference, I was kind of a little bit bored in meanwhile, and I wrote this thingy. It's a search engine, and you can just type there something like, let's say, thread, and it will search C++ draft, and you can just click on it, and it will open for you the C++ standard here, and this is like definition of thread. And I will go back, and you can look for different things like Velociraptor. There is a Velociraptor. Velociraptor, yes. For those of you who didn't know, there is a specification of volatile, because they are like dinosaurs, they should go away, so it's Velociraptor. Anyway, let's go back, and hopefully, sorry, I don't know why this is not going, the tab bar is not going away. And yeah, back. So I did this search engine. This little thingy works like this. It will look at every 3 characters as 3 grams, look at the reverse index, and calculate intersection for all of the index parts, and give you a list of all documents and occurrences of the n-gram you're looking for. And then you will merge them together, and you will get a list of documents sorted by number of occurrences. It's a really simple algorithm, and in JavaScript, you can do it lazily because you don't need whole index. You can just fetch, download only part of the index to do the search on client, because everything is happening in JavaScript on client. So in JavaScript, you will just write fetch URL and await for a result and store it into constant result, and you are done. Easy. How will you do it in C++? Which library would you use? Boost ASIO, you will need to implement your own HTTP engine. Boost Beast, it's mostly for WebSocket. You will probably use curl, but curl is C API, so it won't work easily with strings and everything. So you will probably spend quite a lot of time trying to make something like this in C++. It's hard. Because in C++, we like to work, think about pointers and bits and performance, and this is like, there is a TLS, network API, resolving, and everything. But fortunately, I like library curl, so I decided to use it. But let's go back to JavaScript, because I'm going ahead of myself. You can download multiple things by prefix, and then combine 2 promises from the fetch to 1 promise and return them together. And you can await on them to both to be finished. And even JavaScript in browser is single-threaded. it will run in parallel because it's asynchronous. So you don't know which will finish first. I think that's quite nice utility, and you don't need threads for that. I mean, all JavaScript developers in the world don't know how to do threads because they don't have them. Okay, you have async keyword, which makes your function asynchronous. So it will return promise with something you return from it. And name is the prefix, fetch, and the thing and promise. Actually, I have syntax highlighting, so enter libcurl. How many of you use curl at least once in last month? That's quite a lot. I would say like 20%. Because it's quite nice library. API is actually, even when it's in C, is kind of C++ friendly. And okay, how many of you who at least once use libcurl wrote their own wrapper in C++? Yeah, it's kind of like homework for everyone who is using libcurl. So libcurl is kind of old, older than some of attendees here, and it's a nice simple API, and you can use any protocol. That is a protocol for HTTP, obviously, HTTPS, FTP, but you can also work in FTP and many other protocols, even like IPFS. IPFS is interplanetary file system. It's kind of, Google it, it's interesting. So libcurl looks like this. You will initialize handle, check if actually it's correct because you don't have exception, so you need to check it. And then set options, URL you want to download, and that you want to follow also redirection in HTTP protocol. Then you call perform, which will block you for all I/O. And when it's done, you need to check if it's not error. If it's an error, you need to print the error. We are in C world, so printf. And then release all memory. OK. And if you want to write a result into object, I'm going slowly into C++ world. So I have string. And I have a write data option, and I will provide a pointer to string. And then every time I get some piece of output, I can just append it into string. That's like the modus operandi, what you do with libcurl. And then return size you got, and provide write function, which in my case is a lambda. How many of you know what the plus means in front of the lambda? Yeah, few. It's a explicit casting into function pointer. So easy perform. I call easy perform. Wait for the result. Check for the if I was successful, and throw exception, and return the result. Okay. So I'm writing my own wrapper for curl. So I'm creating my own easy handle with constructor which takes URL, because every time I'm using curl, I'm passing some URL. There is some destructor to release memory properly. There are some options, so I can set another URL later maybe to enable following location, or write into some container which is appendable. It's a template. And I have function since perform, which will block and do the I/O for me. OK. So example, I will create handle, allow following location, provide string to output, write into string, do the since perform. It's explicit, so you know that it will block. And then if I'm fail, throw exception, otherwise return the result. This is probably something which everyone in C++ world who wrote a wrapper around a curl did, something similar. So, but I want to be asynchronous. So I want my function to return some promise of string. I want to await on the perform, on the I/O. And when I'm done, I want to return the output string into the promise. So how many of you use coroutines? 1, 2, 3, 4. Just few. Why? Because they are scary. Why scary? Because standard library doesn't support coroutines yet. Only in 23 you got generator, but nothing like task or promise. It's too complicated. Every time you see talk about coroutines, there is so many customization points and whew. And it's also, I heard this quite often, it's too new. It's actually 4 years old in standard, and it was standardized, it got into standard 5 years ago. It's too new. My friend from unnamed company wrote something with coroutines, and he was in the middle, and then site leader came to him and told him, no, you need to scrap this, and you need to use our own like light straight models because coroutines are too new and they're probably problematic. Wow. Tell me about job security. Anyway, but you can think that functions are just specialized coroutines. Because coroutines can be seen as generalized functions, or functions can be like specialized coroutines. Because function in C++ on any like normal language is just something. It takes something and returns something. It takes something, start once and end once, and will never get back into itself. So they have one starting point, one entry point. They can have multiple exit points. You can have multiple returns, and they behave as a scope. You always put them on top of each other. So it's really easy to have like system stack, which just push something on memory, so you don't need to care about where memory will be like allocated or something. Like this, you have caller, which calls some function, return from function, call another function, return from another function, call another function, and so on, so on. But it's really easy to to see what's the lifetime of your objects and variables in your functions, because they are always in scope. RII is the building blocks on modern C++. But coroutines can have one starting. They have one starting point and multiple entry points. You can start them, suspend them, and then enter them again. So they can be suspended, resumed. They can have multiple exit points as function. But the lifetime of a coroutine can live past your caller. So it's really it's much harder to argue about the lifetime. So you don't know. So I kind of fails. That's the reason actually why coroutines in C++, because they can be optimized and you don't know how many variables will be there and how many variables will survive suspension point. So compiler cannot know how big they will need to be. So that's the reason why they are allocated on a heap. But optimizer is trying to very hard to give you option to actually run them and put them into stack if it's possible. But sometimes it's not possible, especially if the coroutine will survive your caller and you cannot have it on stack. So you need to have it somewhere else. You can have like allocator for that. So it can look like this. You have caller, you call it like generator, and immediately it will be suspended. And then you will resume it. It will run for a while and then suspend it back. Then resume, suspend, resume, suspend. So you can write a generator code. That's like basic coroutine, and it's in standard. You can just write my function, my something, return generator, and coiled, and it will work. You don't need to know what's happening behind. But generator has a property that it will behave kind of as a function. So lifetime of generator is tied to the object in the function you are calling it from. So it's easy to argue about the lifetime. But coroutines, some people think they are like threads. But coroutines are still in one context, in one function, like in one thread. And just sometimes they are suspended and some other coroutines can be run instead. But with threads, you need to spawn thread. And when some I/O is blocking you, it's actually going to usually to kernel and you are blocked, and then kernel will schedule your threads. So they are kind of heavy. Coroutines are much more lightweight. But with coroutines, because there are multiple usage and designs, if you actually write your own coroutine type, you are responsible for that. Because it's like cooperative multitasking, like Windows 3.11. Your application must count with that sometimes some task will be suspended and something else will happen. And that's the reason why it's really hard to create a coroutine type in standard library, because we need to find some general trait which can generalize everything or not, and maybe it's easier to let other libraries vendors to come with other solutions and then look later. But this is like chicken egg problem, because no one is using coroutine because they are no library support, and no one is writing library support because no one is using them. Sorry. So let's say JavaScript function on the left, divide. It's not IO bound, so it doesn't make to do it coroutine, but I did on the right. Divide with 2 parameters, check if it's 0, throw exception, and at the end return the result. The difference is the async keyword on the right function. It returns promise. In C++, it's similar. Let's say divide function, int A, int B, check, exception, and return. In C++, we don't have the async keyword in front of function or some like other mark. And the committee, in its eternal wisdom, decides that we will use co_return, co_yield, co_await. I know it's ugly, but it gives a compiler hints that this actually is coroutine. So it should look for something called promise type of a coroutine based on its return type, function int. In this type, it's my type, which representing this is a function returning int. And because it's co-return, compiler will build some machinery around it. But from caller side, like if you look at the header, there is no difference between normal function and coroutine. Just call it, and it will give you object of type function int. But internally, as it will build, it will spawn coroutine, do something as you describe in the function type. So you need to use at least once co_await, co_yield, co_return to make them defined as a coroutine. And and when you do that, compiler will look for coroutine traits type of your return type, and also of its arguments. So you can specialize also based on the arguments to give different traits. It's a specialization point, and every specialization point for coroutine is there for a reason. They are complicated, and sometimes to understand them, you need to understand all of them, so which is like, again, chicken egg. But I hope I will help you with that. Coroutine traits is just simple struct, which take the return type, arguments, and if there is a promise type as part of your return type, it will use that. That's the default one. So you usually don't need to define your coroutine traits. But you can, and you can create something totally different. It's type name, arguments, and if there is a promise type, and then just provide it. But model of coroutine is a little bit different. You have program stack, and you call your function, something which will give you the function t in my case, which contains only coroutine handle. Think about like void star pointer to coroutine. And the coroutine object itself contains 3 things: resume point, promise type of the function, and coroutine frame. Resume point is address into code where the coroutine will resume when you resume it. And function promise type is something you can, it's user provided by the library author. You can specialize. You can provide some different behavior for exception, for result, how to await on it, what you want. That's the thing you write. And coroutine frame is actually stackless stack of your function. Every variable which will survive suspension point. So anytime you suspend between in lifetime of some object will be put in coroutine frame. And optimizer will try to squeeze it to small as possible. So it can reuse it, memory, and so on. Okay, coroutine handle is just kind of void star thing of size of pointer. And it's provided by standard library. And it contains few functions. It can be typed or it can be not typed. If it's not, the handle can know about the promise type inside, promise type you provide, or it can be just void star. It's polymorphic because it's really useful to combine different types of coroutines together. So you can destroy it because, as I said, coroutines have different type of lifetime, so RII doesn't work. So you as the owner of the owning object of the coroutine handle, it's your responsibility to destroy it. Maybe as a RII, but maybe some it's on that pool. So when it's finished, maybe, or at the end of the program, or maybe even never. Then we have resume function. And if coroutine is currently suspended and you call it, it will resume your coroutine, which means it will, on current stack, create a space for every variable which is unique only for the between suspension points, because that doesn't need to be on the stack for a stackless part of coroutine frame. And it will jump into the coroutine. It will jump. It won't call. It will jump. You can check if the coroutine was finished, which means it reached the end of the coroutine code. I don't want to use function name because it's not function, but it's coroutine. It's also explicit operator bool, so you can just check it and you don't need to call .done. And if it's typed, you can actually access the promise type from it. And you can, from promise type, you can actually get the coroutine handle. At the end, it's just like probably from perspective of the machine code, it's just like it will take address of the promise type and subtract few bytes from it, and will give you coroutine handle from it. And then you can actually take address, so you can actually convert coroutine handle into void star pointer and back from it, which is really useful to when you are interacting with C-style API with UData member. So my function, as I'm implementing my function as a coroutine to show you that it's not that hard, the function type, the one which user interact with, contains some promise type. I will get there later. Contains coroutine handle of my promise type, handle, and it will initialize with the handle. And when it's destroyed, it will destroy the coroutine itself. So function behaves as a normal function, so everything inside the function will be destroyed when the function is destroyed, kinda. And I can access the result with get or explicit casting. So go back a little bit. Coroutine can be kinda, you can think coroutine every time you get it's kinda like lambda. You will have everything which will survive suspension points. It will store in the like lambda capture plus the resume point, and it will store address of the first resume point. And every time you call this lambda coroutine, it will jump to the resume point. First time at state 1, it will do something, and just before it will suspend, in this case implemented as a return, it will store the address of next resume point, and then it will suspend the coroutine, which is just like exit it. And next time you will run it, it will be here, and then another suspend point, and etc., etc. This is like homemade coroutines. And each suspend point in coroutine body is marked with co-await or co-yield. It's a hint that compiler needs to do some transformation of the expression into the suspension point. Every time you call co-await on some expression, it will evaluate the expression and check if the expression is awaitable, call function await ready of the result type. And if it's not ready, that is the result of the expression is not ready yet, then it will mark point after the expression, after the co-await, so it can be also inside of the expression, not just after the part of the expression, let's say, mark as a return point. And then if await suspend function, which needs to be there of the result, returns void, it will suspend current coroutine, store it like, it will suspend and return. It will call the await suspend function and return. If it's suspension point, await suspend return bool, it will call the function, check the result, and if it returns true, it will suspend. And if it returns some other coroutine handle, which means jump somewhere else, it will just jump there. So it's not like function when you go there and go back, go there, go back. You can just go there, and when you suspend, you can just jump somewhere else. So it's more like a graph. And when you are resumed, when finally someone decides that this function, the awaitable we are awaiting on, is ready, that the result of maybe I called .read on socket, when it's ready, and it will resume my coroutine, I will call function await resume, which returns what I asked for. So we have some standard awaitables, suspend always and suspend never. They are like useful build types when you are writing coroutines. Suspend always will suspend you always. It will never be ready. And every time you call it await suspend, it will return void, so which means it will suspend always. And resume is returning just void because it doesn't make sense to return anything else. And never will obviously be always ready, and it will always return void. The await suspend function will never be called. So our function, and inside there is a promise type. There is a function in each promise type you provide, or when you are implementing a library type, which is called initial suspend. When you run coroutine, it will gather arguments, and then immediately it will call initial suspend and co-await on it internally, and decide what it will happen. In my case, I don't need my function to suspend because I can execute it immediately. So I'm returning suspend never. Then there is a final suspend point when the function reach the end, coroutine reach end of its body, or its exception is thrown, or you called co-return. It will call final suspend, and at the end I can suspend always, I can suspend never. In this case, I'm doing suspend always because inside of the promise type I will store the result, and I don't want the result to be destroyed, so I can actually reach it later. Because there is like function get return object. When coroutine is called before there is any suspension, compiler will call get return object after this promise type is built, and you can take promise type created from the handle type from the promise type and build your own function, like your type, in my case, the function. And there is a place I can store a result of my function, and if there is an exception, I can store exception pointer here. And every time I call co-return, compiler will transform it into calling a return value with my result, and I will store the result inside of the promise type to be used later. And when there is exception, compiler will call unhandled exception, and I can store exception pointer or do something else or terminate or log it, whatever I want. Then we go back, and constructor will just take the handle, and it's constructed from the handle. If I destroy the function, I will destroy the handle as I did before, and get will check with assert my coroutine is done. If there is an exception, I will retro it. So it will behave as a function. If I try to get the result from it, it will throw if there is an exception. Otherwise, I will get the result and return to my user. It's a function. It's a function as a coroutine. Everyone knows one function. So let's write function divide with like this thing, like transformed. So I will have function divide, and when I call it function divide, it will return me function int type, because it's a function returning function int, which is kind of just the coroutine lambda, which stores the arguments a and b inside of it. I'm just marking as coroutine frame. It's like pseudocode. Don't use it. Like it won't work. It will first do the initial suspend and co-await on the result, and then it will wrap the body of the coroutine in try-catch block. So if b is 0, I will throw exception. Otherwise, I will call .return value on the promise type, return the result, and jump into the final suspend point. If there is an exception, I will call unhandled exception in my promise type. I provide it. And at the end, I will just do the final suspend and will never go back, because from never suspend always, I will never go back, because this coroutine after that will be destroyed. If you try to resume function, resume coroutine after it reaches final suspend, it's UB. So let's say I wrote cocoroutine promise type. Promise and promise type are two different things. Promise is promise something from cocoroutine, and promise type in this context is the coroutine promise type. But this is just promise. So my promise type will be similar as a function. I have inside I have promise type and I have constructor. I don't want to be copyable, but I want to be movable. I want to destroy it if it's not empty. I want to assign it, and the promise from curl itself is awaitable, so I can actually await on it. So if my handle, my coroutine is finished, then I'm ready, because I return something or throw something. Then if I suspend, and I get argument is some coroutine which is suspending on me, I can look in my promise type, and there is function someone is waiting for me. Someone else, some other coroutine is waiting for me with this argument, and I return something else. So I can jump to do something else meanwhile. And when the coroutine is awakened, I will just check for the exception, rethrow it if there is exception. Otherwise, get the result from outside from the promise type. Okay. So promise type of my promise is just similar as the function promise type, but with few differences. Inside, I have coroutine handle of someone who is waiting on me. So when I finish, when I reach my final suspend point, I can jump to other coroutines. So when I start my coroutine, which is from like associated with curl, I have some schedule, and I inform the schedule I'm going to start. And I will never suspend. I will immediately start the code. And when I'm final suspending at the end of my coroutine body, I will take my promise type, and I will never be ready for the suspend point, which means I will suspend. Then that doesn't make sense, the resume, and await suspend. I will get, when I'm suspending, I'm getting always my handle, my own handle. And I will tell schedule I'm done, but inside of my promise type, I have awaiter, which is awaiting on me. Or maybe it's empty. And if someone is awaiting on me, I can resume them, because result for them is ready. And I will just return my special suspend awaiter. And there is a function, someone is waiting for me, which takes some a polymorphic coroutine handle, store it inside, and tell scheduler, which is like magic thing somewhere else, that I'm going to suspend, and please choose someone else who can still run. So then I have awaiter lazy perform, which will take a curl handle, and it's always never ready. And when I suspend, I will just associate the coroutine, my coroutine handle with the curl handle. I will convert it into void star with the to pointer, convert pointer, I don't remember. And in libcurl there is a private ptr, I think, option, and so you can store just like some pointer in your handle, which is not touched by the library. And then I will tell scheduler, please suspend me, so it will return suspend always, or some other it will return some other handle to run, because I'm telling scheduler I'm suspending, jump somewhere else. And when I'm finished, I will return some result type which contains error code from the curl. So I can check if I co-await on lazy perform, which is just a result of the az handle dot perform. So I can check if it's error, if it's completed, and so etc. etc. So I have coroutine, which is calling my coroutines. So I call my coroutine and immediately start, because there are two types of coroutines, immediate and lazy. JavaScript is using immediate coroutines, so whenever you start coroutine, it will start executing immediately. Python is using lazy one, so they are not started until you ask for the result. In my case, because I love JavaScript, as I said, and it's on record, public record already, I'm using immediate coroutines because as a JavaScript. So my coro1 coroutine will run until it's blocked, because I need to download something. I need to fetch something on the internet. So it will suspend. But in color, it doesn't know what to happen. So schedule will learn about existence of my coroutine and do something with it. But I didn't co-await on the result, so I can start another coroutine, which is also immediate. So I will call it, it will run for a while, it will suspend. And I'm still not co-awaiting on any coroutine, so I can run another coroutine, third one. It will run it, and it will suspend because I'm waiting. So scheduler now knows about three coroutines. Three coroutines started from the perspective of scheduler. And now I will run the caller, and now I'm co-awaiting on the result. Now I actually need the result for something. But scheduler sees three coroutines which are all blocked, or actually four, because caller will be also coroutine, which means everything is blocked, so it must do some I/O. So actually, what it will do, the caller, if I'm co-awaiting on blocked coroutine, it will tell scheduler, complete something for me. Do something for me, because I cannot do anything else. So scheduler will do the I/O, and first coroutine which will be finished, I don't know which one, let's say 2, will be finished, and then when it's finished, everything is still blocked, so scheduler will get another, complete something, some I/O. So it will finish coroutine 1, okay? Coroutine 2 is finished, everything, and then I finally co-awaiting on coroutine 2. And I'm moving forward. Now I'm co-awaiting on coroutine 3. It's blocked. And everything is blocked. So I need to, again, ask scheduler, and it will finally do the coroutine 3, and I'm finished. So you can actually start multiple jobs and actually do the slow work, which is I/O network, later. So scheduler type in my library is kind of easy. You have two variables. One is number of running tasks, number of blocked tasks. When I start coroutine promise, co-curl promise, I will tell scheduler that I'm starting, so I will increment the number of running tasks. when I do final suspend and select next from the coroutine, from the final suspend point, I will decrement number of running tasks and select possible next coroutine. And if I call suspend and select next, I will increase number of blocked coroutines and select something else. And select next, yeah, also here when I'm doing the final suspend, there is the awaiter in a coroutine promise type I'm passing. So if there is something, I'm giving hint to scheduler that this can be run. So select next will take the hint if there is any. And if it's there, I will just decrement number of blocked tasks and run the now unblocked coroutines because it's waiting on something which finally is there. But if there is no hint and number of running tasks is different than blocked tasks, what I will do, I will return no op coroutine, which is special library thingy, which will immediately suspend and it's like return in call tree. It will just go back to to the caller, as I did in the image when I'm blocked and everything is blocked. It's not everything is blocked. Something can be still run, and I will jump to caller of my current coroutine. And when number of running tasks and blocked tasks are same, so everything is blocked, and I need to do the I/O. I'm calling the I/O, and the I/O will return handle of the coroutine, which I associated with the handle, and decrement number blocked, and return the coroutine I get. And because this function will get the handle to someone who's awaiting, I will just jump into the now unblocked coroutine. The complete I/O and return coroutine function I will get there later. So enter libcurl multi-API. How many of you with libcurl use multi-API? A little bit less than with easy-API, because easy-API is really simple. Multi-API is a little bit more complex. But it's actually really simple. You have other handle. You have like a curl multi handle, which is like set of all handles. You can add there. You can remove. And then you can perform over the set of the handles. And after you perform, you can actually wait for something to happen, for I/O. And after something happen, you can actually ask the set if something was finished, and it will give you information about first finished handle. So complete I/O and return coroutine is infinite cycle, which will call perform on the multi-curl API I refer to. And if there is something finished, I will get a raw handle from it and extract the coroutine handle from it and return it. And if something wasn't finished, I will just wait for I/O because I'm blocked everywhere and try again. So when something is finished, when I finally download something or it's timeouted, I will get a coroutine which will wake up. So fetch. I'm making fetch happen. Do you know Mean Girls movie? Okay, crickets. Nothing. It's an awesome movie. It's kind of full of memes. You should watch it. And I'm making fetch happen. So fetch function will take URL as a string because I'm taking the value, and there is a number of attempts. So I can actually try it multiple times, and I will return content of the URL as a string. So I have string with output. I have the easy handle with the URL. I will write into the output string. I will follow redirections. I will try multiple times. If there is no attempts left, I will throw exception. And there can be like exponential backoff, but it's a slideware. But then I will try to co-await on the perform, which will give me the lazy perform, and it will suspend current coroutine and it will jump somewhere else until it's ready. And then if I failed, maybe I tried download only part of it, I can try to just resume and continue like to download the big size. Yeah, sometimes it's useful, sometimes it's not. And if I got a response code different than HTTP 2XX, I will throw exception, it's not available, or sys server error, whatever. And if I'm successful, I will return the output to user. And I made fetch happen. So utilities around it. You can also wait for, if you have multiple promises, you want to download multiple things. Like in JavaScript, you have promise.all. You can just take a range of promises and a return vector of results as a promise. So you take the value type of the range. So what's it returning? You will extract the result of the promise somehow, and then you will just take promises and convert them into vector. And because you need to materialize the promises into some result type, and then you will result the output. And then for each promise, you will iterate and co-evaluate on the results and co-return. This itself is coroutine you can co-evaluate on. So when the result is when a result is ready, every promise of the input is done, ready. You can do it also with like range returning back optionals. If you don't like exceptions, you can have multiple optionals, and if all of them return success, then you will get optional of the successes. Otherwise, it will give you null opt. So it's similar, but if some result will fail, it will give you wrong optional. You will return null opt, and otherwise you will build same vector of results and return it. Then you can have also this function, but you can also have alt tag and create operator pipe, so you can actually interrupt with ranges nicely. So you can take just ranges of promises and just pipe it into all, and it will just pipe it into this function. Same with different styles, with optional, and internally it will just pass the range into the function and return the promise. And you need to create object all, because it's an object, it's not like function, it's just like pipe all, and you don't need to use any braces or parentheses, nothing. So everything together. Let's say if you have a resource with URL and content, you have a function fetch resource, which will take URL, store it into the resource, and download the content, and return object containing address and content. And then you have function fetch all, which will take URL, return a vector of resources. You will co-evaluate on you will download, let's say, web page. With CTRE, you will extract all absolute links. You can pipe it into CTRE. Then you can transform it, because you have only URLs. You will transform it into fetch resource, which will download the resource, create promise of the resource, and then wait for everything to finish. And it will give you a vector of the resource downloaded. In parallel. Yeah. And if you want to write the search engine I did in JavaScript, you can have a search function. You can provide number of results you want. You can just take the text you are searching for, look for the sliding window of engrams. You add also their position, then download all the engrams you want with some function fetch engram and shift the position. Then you can sort them by size, because it's it's an intersection of interset of all the charts. So you want to start with the smallest one. Then you fold them left with first element as the first one with some function index intersection, which will just calculate the intersection. Then you will fold the results again, because you got all the occurrences, document and position. So you will reduce them to actually document ID and count. You can look for only partial sort of top n results, resize it, and return to user. And you write your own search engine based on engrams, which is lazy downloading the index from web. And hello world with Kokoro looks like this. Sorry. You can download two documents, wait for all, co-evaluate, and use structure bindings, and you have hello world. Thank you. And 10 minutes. We have time for questions, so if you have any questions, please shoot. And maybe I will shoot you down, but you can look for the library on my GitHub, and also you can play with the search engine on my GitHub IO pages. No question? At least some.
Might be a stupid question. If so, I apologize.
No question is stupid.
Don't challenge me.
OK.
Regardless, you implemented all to wait for the finishing of all coroutines. How would I go about implementing something like any to wait for the first one to finish?
Yeah, you can, with the same style as if you have like all coroutines, you can actually write, in JavaScript world, it's called select, I think, which will actually associate to like final suspend point coroutine, which will like wait for them and destroy everything else and return the first to finish. It's in the library. It's not on slides because it's a little bit like lower because you need to like poke around. So it's not that clean, but yeah, it's there.
So that would require modifications to the scheduler part.
Sorry?
If I understand that correctly, it would require modifications to the scheduler part?
Yeah, schedule on slides is a little bit easier than in the library itself.
Makes sense.
And it's still in the library. It's not perfect because it's JavaScript. I love JavaScript, so it doesn't think that there is multiple threads yet. So it's like singleton. It will be thread local scheduler. I would love to have like scheduler which will exist only for like call tree of all coroutines you are running. So it will be like a one context, one call tree. But that would need changes in standard.
OK, thank you.
OK, any other question? Yeah?
Yes. So you said you implemented it to perform the operations eagerly?
No, it's immediate coroutines, so they will start immediately when you do something.
Yeah.
And the I/O itself will start in a moment when everything in your call tree is blocked. So it will run everything as much as possible until you need to actually need to wait. It was kind of hard to implement, and I like to try multiple paths. But yeah, I think it's better than because it then just start when you like coroutine you are only waiting for, because this will allow you to actually do parallel downloads, parallel streams of downloads, and in one thread. And for business like business type of code, usually don't need like multiple threads. You just need like download 10 files and combine them maybe.
Yeah. I'm asking because in the senders receivers model, they advertise for lazy evaluation basically.
Yeah, because as far as I know, they are also like running with thread pools, and this is a little bit different. Like there are different models, and both is colorful.
Yeah, one question towards prematurely stopping coroutines. So, for example, in your search engine, user just typed the new letter. I don't want to receive any of the previous search results anymore. I want to now start over the search with my new search string. Yeah,
in that case, if the coroutine is currently not running, which will probably not be the case because if you called the search function, it will start coroutines until it's finished. But if you, from like some side channel, you can put some there like cancellation. If you knew that coroutine is not running, it's safe to call .destroy or its handle, and it will safely remove destroy all the object itself, even like recursively coroutines. Reference it from inside. So if the coroutine is not running, because it's not thread, so if it's running, then you can safely destroy it.
Okay.
But, and this is one thread, so there is like actually like no one else like on site. So with this model, it will need some changes, but it can be also kind of done. But first, you will need to like pause the scheduler, and inside the scheduler, which is outside the coroutine, to destroy the coroutines.
Okay, and then also adapt minorly my code waiting for the promises to stop waiting for it and wait for the new promises.
Yeah.
Okay, thanks.
Okay, so we have one question from the online audience. Is it possible to overload memory allocation either using custom allocator or PMR?
Yeah, you can provide any allocator you want, and it will implicitly use. You can pass it as an argument to a promise type, and you can. There is an operator new for the promise type, and there is also it can be done. It's not that hard, but you need to store the reference to your allocator inside of the promise type, so you will also safely destroy it. So you need to provide operator new and operator delete for your coroutine, coroutine promise type, and that's all.
Okay, thank you.
Okay, thank you. It was fun, and it's a great conference, and enjoy 2 more days of it.